In this video, I'm going to talk about the strength and stiffness degrading SSD model as a continuation of what we have started 2 lectures before, or 2 videos before. And the strength and stiffness degrading, or SSD model, is aimed at approximately reproducing the hysteretic behavior of structures in which lateral stiffness and lateral strength decreases when subjected to cyclic reversals. So the meaning here is, as you can see, and as I explained before, this is the stiffness of the system at each cycle. As you can see here, it is, it is decreasing. As you can see here, it is decreasing. So the stiffness is decreasing, which means the slope of the pattern of the loading pattern, and even in unloading also, it is the same. It is degrading. And we found that in the same time, the strength means that the force, the maximum force or the maximum capacity of the system at different cycles. So in the first cycle, the system strength was here. The second one here. The third one here. The fourth one here, and so on and so forth. As you can see, it is decreasing. It is decreasing. So this is strength and stiffness decreasing. And this is commonly is the right case where that we are having a poorly detailed reinforced concrete. This is a very good hysteretic model for poorly detailed reinforced concrete. And you are going to find that here it is the energy dissipated is much less than the elasto-perfectly plastic model. If we compare it here, for example, with the elastoplastic model or the elastic perfect plastic model, or even if we compare it with the stiffness degradation or stiffness degrading model. Okay, so here it is, as we said, the amount of strength and stiffness degradation is going to be decrease, and in the same time the amount of decrease, whether for the stiffness or the strength, it is a function of the maximum displacement in the previous cycles. So if we say that this maximum strength, it is a function of the maximum displacement in the previous cycle. So if we say that this is the maximum displacement here, so it is a function of the maximum displacement that has been already obtained in the previous cycles, and as well as a function of the hysteretic energy dissipated. And the hysteretic energy dissipated at each cycle here, for example, then it is a function of how much energy dissipated in the previous cycles, for example. Okay, so it is function in 2 different things, and the hysteretic energy dissipated before and the maximum displacement in the previous cycles. This model is similar to a famous model that was provided or presented by Kanath et al. In 1992, okay, called IDARC. Okay. When probably calibrated, this model can reproduce the response of poorly detailed reinforced concrete structures relatively well. And this is very famous case for many of our structures, because we have most of our existing structures, they are poorly detailed. So this means that this model is really very suitable for many kind of reinforced concrete structures which are poorly detailed or designed before the implementation of new and recent seismic design guidelines and codes. Okay, so this is important, and you can keep this in your mind. An example is shown actually in the next slide. I'm going to give this. This is actually an example, a comparison of experimental results. So this is an experiment that has been conducted in University of Washington by Lehman et al. In 2000, and the corresponding analytical model that is being produced here, as you can see, it is well matching for the analytical SSD model. So the experimental model is well matching the analytical model. Okay, as you can see, the load deformation relationship of a poorly detailed beam column joint tested at University of Washington is compared with the response computed with the SSD model. So this is for a poorly detailed beam column joint. Okay, so if you have a beam column joint and it is poorly detailed, which is, as I said, the case of most of our buildings and RC structures, then this model is going to be the most suitable one. Okay, now let's go to the last type of hysteretic behavior, which is the nonlinear elastic model. We call it NE model. As I said before, for the nonlinear elastic model, the loading and unloading path, they are the same, whether for unloading or for loading. So it is the same. It goes back and forth with the same, on the same track, on the same path. The nonlinear elastic model unloads on the same branch as the loading curve and therefore exhibits no hysteretic energy dissipation. Okay, so this is an important thing. So there is no energy dissipation here. The energy dissipation is zero. Okay, this model approximately produces or reproduces the behavior of pure rocking structure. Actually, rocking structure, this is maybe in some recentering systems. I'm not sure that you have an idea about this or not, but in general, it is in many cases where that we are putting some recentering systems, and some researchers already we have like reproduced or produced for this, and many there is a wealth of research regarding this this recentering capability of the structures using walls, for example. This is a comparison between two cases here. A case where that we have a building that is cast in place structure walls are used. Commonly we are using dowels and rebars and so on. Whenever there is external force, we are expecting, as usual, that the plastic hinge region is going to be formed at the bottom of the wall, and we are going to have cracks, shear cracks, as you can see here, right? However, if we are going to replace the cast in place structure wall by a kind of rocking wall, we call it rocking wall, for example, and apply the same external force, we are going to find that this rocking wall is going to be behave as if there is like overturning moment here. We call it rocking for this case. So we're going to find that at this edge, where that we used to have plastic hinge formation in the encast or cast in place structure wall, we're going to find an uplifted edge, or we are going to find, we call it gap here. So this gap is going to take place, and this rocking wall is going to be connected to the foundation using PT strands, post-tension strands, for example. So we have like a unbonded sleeve here, and then, or a sleeve, and then we are putting unbonded post-tension strands that is going to restrain or going to provide the recentering capability of this rocking wall. This is if we put only one strand in the middle. Other types we provide like two different like PT anchorage or PT or unbonded PT tendons, like two of them. And sometimes, because we do not have any kind of energy dissipating protocol here, or any kind of energy dissipation in this rocking wall, so sometimes we use some dowels, like bonded mild steel bars, for example, as we are putting here. We put it in between the original unbonded PT tendons, and we are making the anchorage in the foundation bottom here, and the top we put the PT anchorage, and we are putting the wire mesh of the wall as it is. So we are going to find that if we provide these PT tendons at like two of them here and here, as you can see, these are like, we provide ducts, for example, for them, and this is the wire mesh, and we have the original concrete confinement at the edges of the wall, you're going to find that the gap is going to be formed easily here, and we are going to have a recentering capability of the system, so it wants to bring the whole wall again back. And these duals, which are, we call it the unbonded mild steel bars, they might work, okay? They might work for energy dissipation, but actually in most common cases we are like putting some anchorage, or we are putting some rocking technique or recentering technique, and we provide with it some kind of energy dissipating models like steel reinforcement bars or duals or something. So this system is good in recentering, but it is not good for energy dissipation. So we provide some additional techniques for it, as I showed before. You are going to find a wealth of literature regarding recentering capability and energy dissipating systems in research area and research field regarding earthquake engineering. Most instances of rocking in real structures are a combination of this type of behavior, which we have already mentioned, with one of the other hysteretic types that already we have mentioned before, okay, whether EPP, SD, or strength stiffness degradation that include hysteretic energy losses. Okay, so this is commonly used for rocking cases or rocking systems like walls, for example. Okay, so this actually brings us to the end of this definition of different types of nonlinear or the hysteretic models, and in the next video maybe I will talk about how we can get the relation between the two. I'm going to talk about, the relation between the elastoplastic hysteretic model response, if we say there is a response, and how we are going to relate it to the other types of hysteretic model that already we have mentioned now. So we are going to have different responses, and we are going to compare it with the reference hysteretic rule maximum response. This is maybe in the next video. Anyway, thank you for listening, and see you in the next video.